we had a little bit of homework last night on the magnetic force on current carrying conductors. In other words, there's a wire in a magnetic field. There's force acting on that wire. We learned that the magnetic force acting on a wire that carries a current is F is equal to ILB. Now, I would stand for the electric current, L would stand for the length of the wire that's exposed to the magnetic field, B would stand for the magnetic field strength, of course. There is, although we don't usually have to worry about it, there is this little perpendicular sign there as well that indicates that the wire has to be perpendicular to the magnetic field, otherwise all bets are off and this equation doesn't work. Now, there also is a force acting on the individual particles, the individual electrons that are moving within the wire. That force is still F is equal to QVB. I doubt that you'll ever have a question where you're asked to find the force on an individual electron within the wire, but if you are, that's what we do. Okay, understand that there's a force on an individual electron that is this. There's a force on another individual electron that is this. There's a force on another individual electron that is this. All of those forces combined provide for me the force on the wire, which is this. I saw yesterday, I think it was in period 3 class, I saw yesterday a little bit of confusion about why the wire experiences the force. Somebody asked me after class, or was commenting to me after class about, isn't it kind of neat that ferromagnetism works this way? When you have a wire that's ferromagnetic, it ends up being deflected, and it ends up, the motor effect takes place, whatever. And I clarified that with that person, but I want to make sure that you guys are clear on that as well. We're not talking about a ferromagnetic wire here. Okay, we're talking about probably a copper wire that's not ferromagnetic at all. Okay, there's no magnetic effect in the wire. The magnetic effect is caused by the moving particles. Does that make sense? So, I mean, if you could have charged particles moving through a piece of paper, the piece of paper would experience the exact same effect. It's independent of what they're traveling through. It's the moving particles that generate a magnetic field. They're exposed to the external magnetic field. They experience a force. And because they're inside the wire, well, they drag the wire along with it. That force that's acting on the wire, F is equal to ILB. All right. Charged particles normally want to go in a circle, right, when they're exposed to the magnetic field. They still want to go in a circle here, but they can't because they're inside that wire. So there's not going to be, like there was along with this, there's not going to be the FC is equal to mv squared over r up here. It's basically just this equation. And I think you find in one of these questions, m times g goes along with it. You'll see when that occurs. All right, let's take a look at these 2 questions, please. Any issues with number 1? Number 2? 2? Okay. 2 says a thin conducting wire that's 0.75 meters long has a mass of 0.060 kilograms. I'll tell you what, often in these questions, you're going to see the mass of the wire given to you not in kilograms, but in grams, because that tends to be the convenient number, or the convenient unit to give it to you in. But we want to be in the units that we're in right now. We want to be in kilograms. So if you are given the units in grams, which is pretty common, make sure you remember to convert that to kilograms as we have here. What's the minimum current required in the wire to make it float in a magnetic field of magnitude 0.15 Tesla? Forget about finding the minimum current there right now. Let's figure out why it would float. What would cause this wire to float? By floating, of course, we mean not going up, not going down. It's just kind of hovering, floating, hovering, okay, suspended. Good, good, perfect. I'm glad you didn't say anything more to that either. Just stop it right there. Okay. There's equal forces acting in opposite directions. We have to have balanced forces, right? In order for something to not move at all, we have to have balanced forces. Clearly, we have a magnetic force because we've got a magnetic field. So there's a magnetic force that something has to balance with. What is that something? What is that something else that will balance the magnetic force for us, that will equal out and cancel the magnetic force for us? Probably going to be gravity, right? So let's do that. Let's set the magnetic force that's presumably going to be upwards here, right? Because it has to counter gravity, which is going to be downwards. The magnetic force acting on a charged particle would be QVB, but we're not looking for the force on a charged particle. We're looking for the force on the wire itself. that's due to all of those forces on the charged particles. So the equation we're going to use here is ILB. Notice that I've written it as an uppercase L. Usually in your book, on your data sheet, it's written as a lowercase L. I just don't want you to, if I write a lowercase L on the board, it's going to look like a 1, right? So I'm going to always write it by hand as an uppercase L. Don't think that it's a different equation. It's the exact same equation, means the exact same thing. Okay, I'm just writing it so that you understand that it's an L, not a 1. F is equal to ILB, but F is also equal to M times G. These two forces are equal in magnitude, opposite in direction, but equal in magnitude. We're looking for the current that's required here. We're looking for I. So I would be equal to mg over L times B. My mass here is 0.060 kilograms times 9.81 meters per second squared. We're not going to put the direction in there, the negative in there, because, again, we're only looking at the magnitudes of these forces, not the directions, right? Because they're opposite in direction. If we're going to include the direction, then we should have said ILB is equal to negative m times g, because they've got to be opposite. Just look at the magnitudes. Divide that by the length, which is 0.75, times the magnetic field strength, which is 0.15 Tesla. When we calculate the current there, I believe we should get the answer that's there. I think that's right, 5.2 amps. Can't remember who asked me for number 2, but is that okay for whoever did ask me for 2? What was the issue with that? Anybody want to volunteer? People not recognize to set those two forces equal? Was it a rearranging issue? Was it a punching it into our calculator issue? All right, well, thanks for your participation. That was great. Okay there now? I want to take a look at 2 quick numerical response questions. We won't bother submitting these. Let's just do question number 85 first, okay, yourself at your desk. We'll take a look at it, and then we'll do question number 86 individually, and then we'll take a look at that one. All right, let's take a look at number 85 here now. 50 centimeter long length of wire, circle the centimeters because we don't want centimeters, has a weight of 0.389 newtons. What does that mean? A weight of 0.389 newtons. Second, is your hand going up there? No? All right. Good. So that's the force of gravity acting down on it, right? I'm going to just make a little note about that because it's phrased a little bit differently than we normally see. Oftentimes it'll say the mass of it is whatever value. This is the mass times 9.81 already. It's the force of gravity already. There's a current of 0.250 amps. The wire remains suspended. That's a key word there, right? Placed perpendicular across the magnetic field. The strength of the magnetic field is what? What are we going to do with this? What are we going to do? Not sure where to start? All right, we'll start with something that you know. Tell me something about this question that you know. I don't care if it's going to lead me to the answer or not. Just tell me something that you can start with that you know. Yep. Okay, perfect. So you're going to have 2 forces that are equal to each other if it's suspended. Got to be. Okay, so it's a matter of which 2 forces are going to equal each other. Well, we know one of them, right? What's one of the forces involved here? We're dealing with a current in a magnetic field. One of those forces is going to be what, Bo? I'm sorry? Okay, force of gravity. Okay, that's not the one that I was thinking, but absolutely. The force of gravity is going to be one of them because we're told that there's a weight of 0.389 newtons. What's the other force that's going to balance it out? Yep, the magnetic force. Good. We know that one because, of course, we've got the current, we've got the magnetic field strength. There's going to be a magnetic force. The magnetic force on the wire is ILB. Careful not to make it QVB. That's equal to M times G. But the value of M times G, we already know. So we don't need to even put in the variables there. Let's just put in the value, 0.389 newtons. A little bit easier than question number 2 that we just went over, right? Because we've already got the value. Save ourselves one calculation there. We're looking at the magnetic field strength, so it's going to be B is equal to 0.389 divided by I times L. So 0.389 divided by I, which is 0.250 times 0.50. And what do we get when we do the math on that one? 2.11, 3.11 times just 3.11 then, hey? Yeah. So we'd express that, as just 3.11, 3 digits. Always look here, right? They always tell you how many digits. So if you're ever unsure, they always tell you how many digits you're going to fill in. All right, let's take a look at 86 then. Okay, take a couple minutes to do 86, and then we'll look at it as a class again. All right, let's take a look at this one now. This one's pretty straightforward, right? One thing you got to be careful of here, 75 centimeters here. So wire that's 75 centimeters long, current of 6 amps, right angles, perpendicular. We know that that's going to be the case. Magnetic force of 0.35. We're looking for the strength of the magnetic field. So it's just going to be F is equal to ILB, right? And we're going to solve for the magnetic field strength, which is going to be F over I times L. We got the value of F, 0.350, divided by 6.0 amps times 0.75 meters. Now, get a bit of a break in this one, right, Simon? Get a bit of a break in this one, in that if we forget to convert to meters here, if we go centimeters, we're still going to get the same value of B, right? So we're actually going to get away with that. If we make that mistake, we're not going to get this question wrong. But we don't want to get in the habit of that, because oftentimes this question would be asked in that A decimal B's times 10 to the CD format, as opposed to B times 10 to the W. What is the value of that? 0.08, exactly. Okay, so we want the value of B to 3 digits. So it's actually going to be 8.00 times 10 to the negative 2. We'd fill that in as 8.00. Now, if you, what did you get if you left that as 75? What would you have gotten? 10 to the minus 4, I think. 8.00 times 10 to the minus 4. If you fill that in, you'd also get 8.00. Okay. Don't make that mistake though, because again, if they ask it for A decimal B, C times 10 to the D, then you're going to get, then you're going to fill it in as 8.002. Yep. 7.78. All right, he made a mistake. Oh, that's embarrassing, isn't it, Bo? 7.78 times 10 to the negative 2. So we're going to say, fill that in as 7.78 then. Good. All right. Take a look at this for a second. This is what we've been talking about here is in reviewing here and checking over questions here is called the motor effect. We addressed that yesterday when we looked at electromagnetic induction. We said that was called the generator effect, okay, the opposite of the motor effect. The motor effect is called the motor effect because in essence, it's what allows an electric motor to work. An electric force, a magnetic force acting on a wire that carries a current. Take a look at the diagram up here. It's pretty simple. The diagram up here consists of two permanent magnets. It's the red one and the white one, a north pole and a south pole. Obviously, there'd be a south pole over here somewhere, right? Because you can't have a monopole. They're just showing you the section of the magnet that's really relevant to what we're doing here. So you got a north pole, you got a south pole. You also have a loop of wire that we call the armature that loops around there. That armature is attached to this thing that's called a commutator. Sometimes we actually call it a split ring commutator. So what that means is that there's a little gap in the middle here that would be filled with plastic or some kind of non-conductor. So the armature, the wires here are connected to this commutator, but the commutator is split by this non-conducting material. This commutator is touching these two brushes, but not connected to these two brushes. So in other words, it'll rub up against them, but it's not joined to these two brushes. These two brushes, however, are joined to this battery right here as they go around this circuit right here. So how does this work? How does this electric motor work? Well, right now, you got an electric current flowing this way, clockwise around here. It's going through this circuit here. It's going to go through this brush. It's going to go into the commutator because there's the conducting part of the commutator touching the brush. It's going to go around here, around here, around here, okay, back through the commutator, back through the brush, and then back to the battery there. There's a complete circuit formed there, right? So what happens with that complete circuit? If there's electrons flowing this way, and there's electrons flowing this way, what's going to happen to that wire? We'll call it wire 1, 2. And what's going to happen to this wire? We'll call it wire 3, 4. What's going to happen to wire 1, 2? Well, there's a current going through it, and it's exposed perpendicularly, exposed to an external magnetic field. It's going to experience a force. What's the direction of that force? Well, thumb into the board, fingers in the direction of the field. The force on that's going to be which way? If this is my loop of wire right here, let me label this here. This is my loop of wire right here, this piece of paper. The current's going this way from 1 to 2 and then around to 3 and 4, but there's a magnetic field going this way. We're going to say thumb in the direction of the particles, which is this way, fingers in the direction of the field, which is this way, palm's going to point upwards. So there's going to be a magnetic force on wire 1, 2 upwards. It's going to be deflected upwards. But let's take a look at wire 3, 4. There's a current coming out of the page or out of the board for wire 3, 4. Thumb in the direction of the particles, fingers in the direction of the field. There's a force acting on that one downward. So there's a force upward on wire 1, 2. There's a force downward on wire 3, 4. What does that cause? That's what we call a torque. A torque is a force that acts a certain distance from a pivot point. The further it acts from the pivot point, the more torque you get. When I apply a force on the doorway, a certain distance from the pivot point, the doorway starts rotating. If I apply it a further distance from the pivot point, it's easier to cause it to rotate, right? There's more torque acting on the door. Well, when I apply a force on this wire away from the pivot point, which should be in the middle, this starts rotating just like the door starts rotating. So it turns like this. But when it gets to this point, what's going to happen to it? Then this whole split in the ring comes into play, right? Because now the split in the ring is touching the brushes. So now there's no current flowing. So we got a quarter of a rotation because wire 1, 2 is pushed up, wire 3, 4 is pushed down. A quarter of a rotation. Now the split in the ring is touching the brush and there's no current forming, there's no force. But it keeps moving because of inertia, rotational inertia. So it's quarter of a turn because of forces, and it keeps going because of inertia. Now it's like this. Now notice what the orientation of this is. Now on the left-hand side, it becomes 4, 3, 2, 1. As you see that with the piece of paper that I have that's representing this wire here. Okay, 1, 2, 3, 4 becomes 4, 3, 2, 1. Now the current is still going to go through clockwise, but the current is now going to go in reverse direction through the wire itself because the wire is flipped over. So now it's going to go through 4, 3, then 2, then 1. The force on wire 4, 3, which is now on this side because it's flipped over, is going to be thumb, fingers upwards. On wire 2, 1, it's going to be thumb, fingers downwards. So wire 1, 2 did experience the upward force. Now that it's flipped over to the other side, wire 3, 4 experiences the upward force. Goes a quarter of a revolution. Okay, current stops, keeps going because of inertia. Okay, current reverses, causes 1, 2 to be pushed upwards, and so on. What's the net effect of that? What happens to this loop of wire that we call the armature that I'm representing with this piece of paper in my hand right now? It spins, right? Attach a drill bit onto the end of that armature. What happens? You can drill a hole in a piece of wood. Attach the brush on a toothbrush onto the end of that. What happens? Well, the brush on the toothbrush rotates. Brush your teeth. Attach Mixmaster blades onto the end of it. What happens? You bake a cake. You mix the ingredients for a cake and you bake the cake. Okay? Anything that spins electrically because of electricity is based on this principle. It's an electric motor. Now, sometimes you might want it to spin a little bit faster. Sometimes you might want a little bit more torque, right? A little bit more torque as opposed to just necessarily speed. You can get a lot of speed without a lot of torque. Okay, you want a lot of torque because you want it to drill through that really thick, really dense piece of hardwood. You need some more torque. Now you want to have the force acting a little bit further from the pivot point, so your armature would be a little bit wider. Okay. You want to make it spin faster? What are you going to do? What are two ways that you can make this thing spin faster? In fact, what are three ways you can make this thing spin faster? That's your hint right there. There's not two, there's three. What's one of them? Good. Increase the amount of current. So instead of being a battery that produces this much current, it's a battery that produces 30% more current. Okay, what's that going to do? Well, that's going to increase the strength of the magnetic force acting on these wires. And if you increase the strength of the magnetic force, what's going to happen? It's going to spin faster, right? Yep. Good. Make stronger magnets. Okay, stronger magnets is also going to increase the magnetic force acting on these wires. What's going to happen? It's going to spin faster because you get bigger force. What's the third one? Increase the magnetic field, increase the current. Both good answers so far. What's the third and final one? What's the third factor that affects magnetic force? You guys know this. Length, who said that? Good. Length of wire. You're not sure what factors affect a certain variable. Look at the equation. It doesn't have to be necessarily this equation and this relationship. Whatever relationship it is, look at the equation. What affects it? Current, magnetic field, as these two guys already said. As Maria just said, the length affects it as well. So how would you make the length of it longer? Well, what you'd probably end up doing is making more than one loop around. So there's one loop right now. It goes around like this. You could probably loop it around like this, except a little bit neater. So that you got more wire in there. What wire matters? Well, this does, because that experiences a force upwards. This does, that experiences a force downwards. What about this? Does this wire matter? Why not, Daniel? It's in the field. Yeah, it's in the field. Why doesn't it matter, though? Because it's parallel to the magnetic field. And if it's parallel to the magnetic field, what's the force acting on it? Zero, right? So it's this part right here, these two green circles right here that are perpendicular to the field. That's the only thing that matters. This is kind of just wasted wire here, but it's got to be there, right? It's got to be there in order to finish off that loop. Does that make sense? Again, how many times now this year have we looked at applications like, you know, the electrostatic fence painter, or the electrostatic precipitator, or, you know, whatever the case may be, the electric motor in this case? It's really more of a magnetism thing than an electricity thing. Okay, this is not a curriculum objective any more than those things were. Okay, should you spend an hour tonight studying the electric motor? No, you shouldn't. No, you shouldn't. That's not a direct curriculum objective at all. Could you see something like that tomorrow or on a diploma exam coming up in a couple months? Sure you could. It's possible, but you're no more likely to see this as an application than you are some other application that you've never seen before. Okay, we give you these not because I want you to remember this. We give you these because I want you to be able to work through new ones that you haven't seen before. All right? All right, real quickly, guys, we spent some time yesterday looking at the opposite to the motor effect, which is the generator effect. Okay, the generator effect says instead of electricity causing movement, we're going to say that movement causes electricity. So electricity causing magnetism, essentially, magnetism causes electricity. If you have a wire with a current going through it, and it's exposed to an external magnetic field, there will be motion produced in that wire. Okay, that's the motor effect. If you have a wire that doesn't have a current going through it, and you move that wire, you will cause a current to go through it. So this current causes the motion, the force. This motion of this wire, because we pushed it, whether we pushed it with our hands or steam was rising or whatever, is causing the electric current. Again, we call that electromagnetic induction. The reality is, it doesn't matter whether we move the wire or we move the magnets. In both cases, you're going to get a current produced in that wire. Hook it up to a light bulb, light up the light bulb. Hook it up to the power grid, and all of a sudden, you power your house. We see this in a million different places. In just about every bit of commercial electricity generation, everything except for solar power, and solar power isn't used certainly widespread. Okay, it's used locally on people's roofs sometimes, although not very often. There are some commercial power generators that are based on solar power, but not very many. Okay. Everything else is based on this principle. Somehow, we got to move the wire or we got to move the magnets relative to one another, and that's going to generate the current. A real generator, essentially, we won't go into the details of that generator, but a real generator is essentially what you see right there, except backwards. Instead of having a battery there, you'd have a light bulb there. No current flowing through there, not going to cause motion of the armature, right? So what do? We have to move the armature. When we move the armature, we cause electric current to start flowing. So it's, again, the exact opposite process. All right? You guys feel comfortable with that? All right. We just finished our demonstration with the copper tube, and Daniel wasn't able to catch the little steel thing that he was dropping, but yet Tom and everybody else was able to catch the little steel thing that they were dropping. The reason being, that copper tube is a conductor. So we got this copper tube right here that's a conductor. We drop a piece of steel through that conductor, it falls at a rate of 9.81 meters per second squared. There's no reason why it should fall at any rate less than 9.81 meters per second squared. There's no difference between dropping it in the copper tube or just dropping it in thin air right here. The acceleration of that piece of steel will be 9.81 meters per second squared. So why is it then, when I put not a piece of steel in that copper tube, but rather a magnet in that copper tube that's exactly the same size and shape and weight, that it will accelerate at a rate of, say, 1 meter per second squared instead of 9.81 meters per second squared. Copper is not ferromagnetic. This little blue magnet is not attracted whatsoever to the copper. So why does it not fall as quickly? Well, what happens? We learned this yesterday. What happens when you have a magnet and you have a conductor moving relative to one another? Doesn't matter which one you move, right? Doesn't matter whether you move the wire, the conductor, or whether you move the magnet. What happens? You guys know this, right? You got a magnet and you got a wire. Move the wire. What happens? You generate what? A current. We're not moving the wire here or the conductor, the copper tube. We're moving the magnet. It doesn't really matter though, right? I told you yesterday, if you move one, move the other, it doesn't really matter. You get the exact same effect. So what happens here? We're going to generate a current in that copper tube. Now, it's a weak current. Okay, I was holding it. I didn't feel a thing as I was holding that copper tube. Okay, I would have no idea that there was an electric current produced there just by feeling it. There's no sensation whatsoever. But there is a current produced. But earlier on in the unit, we learned something that Oersted taught us. Oersted taught us that a current produces a magnetic field. So we've got two things going on here. We've got, when we drop this magnet, we've got that movement, okay, causing an electric current, or a magnetic field produces an electric current. That's was Faraday and Henry, what we learned yesterday, right? But we've also got what we learned a couple of weeks ago, that an electric current produces a magnetic field. That was Oersted. This was the 1831 discovery. This was the 1819 discovery. Now we got two magnetic fields, though. We got the original magnetic field that we started with, the magnet that we dropped, and then we have a new magnetic field that was produced by the current. Those two magnetic fields will always act to oppose the motion. They always act to oppose motion. So in other words, if gravity is pulling it downwards, then that magnetic force that acts between those two magnetic fields is going to push upwards. If there was some force acting sideways, then that magnetic force would act sideways in the opposite direction to oppose the motion. Why is it always opposing? Well, because it would violate a pretty fundamental law if it didn't oppose it. The law of conservation of energy. Imagine what would happen if you were to stick a piece of a magnet, stick a magnet in a copper tube and just give it the tiniest little bit of push. And its motion wasn't opposed, its motion was added to. This contributed to the motion. You've just built an incredibly simple and incredibly powerful weapon. Think about that. Here's my copper tube. I take my magnet, I put it inside, I give it a little bit of a push. The motion isn't opposed, the motion is helped. This thing shoots out the other side way faster than I ever put it in the first side at. It's a bullet. You can't do that because motion can't come from nothing. You can't create energy. And if it caused it to accelerate at a rate greater than 9.81 meters per second squared instead of less than 9.81, you'd be creating energy from nothing. You start with a certain amount of potential. You got to end with either the same kinetic as you started with potential or less, not more. So it comes down to really nothing new here. What I've just shown you comes down to nothing new. It comes down to two discoveries that we've talked about in this unit. The first one being Faraday and Henry, what we just learned, ironically, a day or two ago. Yesterday, I guess it was. You move a magnet through a conductor, you make a current in the conductor. Electromagnetic induction. But it also comes down to the discovery that was made by Oersted a couple hundred years ago. The electric current makes magnetic field. The electric current you just made makes a new magnetic field. Now you got two of them. Magnetic field number one, magnetic field number two. They interact with each other so as to oppose the motion. If it wasn't opposed, the law of conservation of energy would be violated. That can't happen. You can't create something from nothing. You can't create energy from no energy.